All right, thank you. Good afternoon. My name is Tristan, and I was asked by one of my colleagues, Lee McHugh at Virginia Tech, to prepare an online lecture on the topic of ship roll motion control. So this presentation I'm going to give is based on a plenary address that I gave in 2010 at the conference on control applications in marine systems in Germany. Okay, so as part of the motivation is that roll motion can significantly affect the performance of marine vessels, and the effects of roll motion on the performance of the vessels appeared around the 1800s. Mid-1800s, that was the time when the sails were being replaced by engines, and at that time also there was a radical design into the shape of the hull. So we went from broad hulls into a more narrow beam hull, so therefore they will be more susceptible to be disturbed by roll motion. So since that time there have been many devices that have been proposed to try to attenuate roll motion. They work in different ways, and most of these devices required control system design, and there is a tight interaction between the performance of the device and the control design. So, and it's very easy to fall short of performance if the control design is not done correctly, or if the design of the actuators to attenuate roll motion is not done correctly. And this is due to, there are fundamental limitations due to the dynamics of the vessel about what we can do. There can also be limited actuator authority, that means there's not enough forces to be able to counteract the roll motion. And also some of the things that complicate matters in this particular problem is that the power spectral characteristics of the disturbances can change significantly, and this is due to the sailing conditions. Depending on the heading relative to the waves and depending on the speed at which the vessel travels, we can have significant change in the spectrum of the wave-induced forces, and that makes the design of the control system for roll control a little bit challenging. So, in the next 40 minutes or so, my lecture, I will separate it into 4 components. In the first part, I will talk about, in general, what are the devices that are commonly used to actually do control of roll. I will talk about the working principles, the performance, some historical aspects, and then I'll talk about some key aspects of vessel dynamics in relation to the design of motion controls. And finally, I'll talk a little bit about control system design, and I have a few slides on a research outlook. You know, in the recent years, there have been some new devices have been proposed for roll motion control, and I believe there are still some unsolved problems in which we need to work on. Okay, so just to move on into the first part, into the different devices for ship motion control in roll. So the first thing is performance. You know, what is the objective? Obviously, roll angle can affect the performance of both the crew and the operation of certain equipment on board. But also, equally important is the roll accelerations. So there's a nice story of a vessel, I think it was in the US Navy, that was modified. It was an aircraft carrier, and the objective was to get roll angles of certain values. And the vessel was modified, but then became so stiff that the accelerations were too high for the operation of the aircraft on deck under certain sea conditions. So it's actually, when you design the control system to attenuate roll, you have to take into account not only that the device needs to reduce roll angle, but also it needs to reduce roll accelerations. That's important. So let's move on a little bit to the different devices that we can use to reduce the roll motion of the vessel. One of the early devices that was proposed by William Froude in the mid-1900s was actually the bilge kill. So these are just small kilns that are located along the hull. They have a very poor performance instead of a roll reduction. The reduction is only 10 to 20%. I'm talking about RMS value of roll motion here. Advantages, well, they have low maintenance, they're passive, so they require no control systems. They don't occupy any space within the hull, so that's an advantage. A disadvantage is that they increase hull resistance when roller stabilization is not needed, and also that not every vessel can be fitted with bilge kills. For example, an icebreaker cannot be fitted with them because they will damage very quickly. So this is one of the most basic roller stabilization devices that you can find in some vessels. Another type of device is a U-tank. So basically it's a water tank that is located in the vessel. It's got a U shape, it's got a compartment or a reservoir on the port on one side of the vessel and on the other one, and it's connected at the bottom by a duct. So the idea is that the fluid can actually travel from one side to the other. And the tank is designed, is dimensioned, such that the natural frequency of the fluid moving inside the tank matches the natural frequency of the vessel. Now you can do that only for a single frequency. So what happens is the way the tanks produce the roll motion is that when the waves are on one side of the vessel, normally the column of fluid is on the same side, so therefore you have an increase of pressure in the hull, which produces the moment that induces the roll motion. In this case, would force the vessel to roll in that way. But at the same time, because you have all the water on this side, you have weight due to gravity that try to compensate that force. And by the time the waves move to the other side of the vessel, the water has traveled also to the other side. So that's a principle of working. You can achieve this condition that the water moves out of phase with the motion of the vessel only for one particular frequency. So normally the design of this tank is done such that you design the tank for a frequency that is a little bit higher than the vessel natural frequency, and then what you can do is delay the way the water flows from one side to the other by controlling the airflow from the top. So there are these tubes here, control the airflow. There are some valves that can stop the water or allow the water to circulate by displacing air. So by doing that, we can actually extend the frequencies at which the tank can actually work well. So in terms of performance, you've got roll reductions between 40 and 50%. It can be passive, that's when you do just the design of the tank for the roll natural frequency, or it can be active, which means that based on the sailing, on the particular conditions of motion, there can be a control system acting on the valves that control the passage of air from the top sides of one reservoir to the other. So therefore it can be active. A good characteristic is that the capacity to attenuate roll is independent of the vessel speed. They can also be used to compensate heeling. Disadvantage is that they're heavy, they occupy large spaces, and also because you have a free surface all the time, you need to take into account that for the stability of the vessel, because it reduces the metrocentric height of the vessel. Another type of device that was proposed in the early 1900s is a gyroscope. So the idea of a gyroscope is to use the angular momentum of a very large spinning wheel. So therefore, as the vessel moves, it produces the gyros to precess. I will go into a little bit more detail as we advance with the lecture. They had a very good performance, which was independent of the vessel speed. The first device, it was actually passive. It was proposed by Schlick in Germany. And although it provided very good performance in some sailing conditions, it was hard to adapt to changes in the sailing conditions. And the the Sperry company in the US produced one which was actually active instead of passive. So the Sperry device had a little sensor that measured the motion of the vessel, and based on that it commanded an electrical motor that forces the gyro to precess. And that had better performance. It was also once installed in a Japanese aircraft carrier. They had 95% roll reduction, so it's one of the best stabilization devices in terms of performance. One of the problems they had is that they can introduce a lot of stress and strain on the structure. Then there were some developments around the 1910s and 1920s where they have two twin gyros. So when you have a single gyro, whenever you have pitch motion of the vessel, you can have interactions with the heading. So the idea is to use two gyros counter spinning, and therefore by doing that you break the coupling with the heading. And then in the later years, in the past few years, there's been a lot of reignited interest in gyro stabilization, and this has been mostly driven by applications when the vessel is actually at zero speed, it's at anchor, motivated by the luxury yacht industry. So at the moment we have a few companies in Europe, Australia and the US where they're actually providing designs for gyroscopic stabilization of vessels at zero speed. Another device that is very commonly used are fin stabilizers. Again, these have very good performance, between 60 and 90%. Obviously the performance to a certain extent depends on the speed of the vessel, and the control, design and also the location of the fins on the hull has a significant bearing on performance. They are easy to damage, especially if you have fixed fins. An option is to have retractable fins, like the one that I'm showing here from Rolls-Royce. In this case, the fins can actually be retracted forward and it gets hidden inside the hull. So the fins are only taken out when you actually need it. So this is very common in very large cruise liners. So the fins are taken out while they're at sea, but once they get into the port, they're actually folded in to maneuver in port. Okay. They're one of the most expensive stabilizers to install on the vessel, and for some applications they can produce interference, for example noise affecting sonar. And they also suffer from a condition which is called dynamic stall, which I will stop later. I will talk about that later on. Another device that's been used is actually the rudder. Because the rudder is located below the center of gravity. Whenever you move the rudder, you not only produce moment in heading, in yaw, which is the intended function of the rudder, but you can also affect the roll. And this is an example of if you put the rudder to starboard here, then the initial force, you have an initial force produced by the rudder in that direction, and that will produce the vessel to roll in that way. But then as the vessel starts turning, the vessel turns like a car, so it actually rolls outwards, because there are hydrodynamic forces appearing on the hull that are responsible of the turn. So this is an example here of an aircraft carrier on a steady turn. This is what it is in this situation. And if you monitor the roll angle during this type of maneuver, when you put a step, for example, in the rudder, you will see that first the roll angle will go in one direction, and then it slowly will come up and moves into the other direction. So this is something very important for control design, which is called that the system has a no minimum phase characteristic. So whenever you put a step, the system responds first in one direction and then eventually responds into a different direction. And this, in the case of rudder roll stabilization, is what actually enables to be used, but also limits what you can do in terms of control, in terms of performance. So in terms of performance for this type of device, you got roll reduction between 40% and 70%. Obviously performance to a great extent depends on the vessel speed. The control is very important. It's probably one of the most complex systems to control in terms of roll stabilization of marine vessels. In some cases, you may need to upgrade the rudder machinery to be able to produce fast rate motion of the rudder, and as we'll see later on, the fact that the dynamics of the vessel in roll at no minimum phase from the rudder, using the rudder as an input, that has a significant bearings on control design. So I'll talk a little bit about that later. So let me talk to you a little bit about some of the history when these devices were first proposed. So the first proposal for bilge kills was done in the 1870s, and that was done by William Fruit, who was one of the first people who actually started studying roll motion. Before Fruit's studies on roll motion, it was believed actually that the waves hitting the vessel produce a roll, and it was Fruit actually who came up with the concept that, well, no, it's the changes in pressure that actually produce the roll motion. Then in the 1880s, the water tanks were proposed. In the UK, they were doing some tests on damage stability of vessels, and they realized that when the compartments of the vessels were filling in with water, if they have the right amount of water, it produces a roll stabilization effect. And that's when William Fruit proposed to use water tanks. So this is just a simple tanks located across the vessel with a big free surface. There's been also proposals to actually move weights from one side to the other. There was a French vessel, and somebody put basically a rail across the vessel, and it can move a cart from one side to the other. So in essence, the effect is very similar to the U-tank type of thing, but this one was working with weights. And the first gyro stabilizer was proposed by Schlick in the 1906, and there was another attempt from moving weights in France, and this was not going very well because it actually they lost the control of the weight and actually damaged the hull. Then the first U-tank water stabilizer was proposed by Fram in Germany, and then Sperry came up with the first control gyro stabilizer. And there was a French destroyer was fitted with double wheel gyro stabilizers. The fin stabilizers were first proposed in Japan by Motora, and also were used in Italy. However, the widespread of fin stabilizers became after the war due to the work of the Denny Brown company, which is then known as Brown Brothers, and is now owned by Rolls-Royce. And then the rudder roll stabilization, that's something where it started, some experiments started in the 1970s. And the idea was triggered because during a crossing of the Atlantic of a cargo ship, the autopilot had a very badly tuned wave filter. So when you're doing a crossing of the Atlantic, if you have a heading autopilot, you wouldn't like the rudder to correct the motion for every single wave. So what happens is that you put what's called a wave filter. So the measurements of heading angle are filtered such that the rudder is not responds to every single wave, but only to low frequency corrections. And what happened is that autopilot was badly tuned, and people realized that it was the autopilot who actually was inducing significant amount of roll motion. So that's when the idea of using the rudder for simultaneous course keeping and roll stabilization came up. However, it was the first successful trials were done in the Netherlands on a small vessel in 1972, and then in 1974 there was also a lot of a successful approach to use this device across the Atlantic. Okay? So I gave Lee a paper where I discuss a little bit of the history, but this is also taken out from my book, so you can look at a little bit of the history. Okay, so now let's move to what are the key aspects in terms of vessel dynamics that are important for control design. So, well, we consider the motion of the vessel normally as 6 degrees of freedom. So we have a rigid body and we have a local coordinate system, geographic coordinate system, normally fixed to the free surface of the water. And then we have a coordinate system fixed on the vessel, and we have a point of reference OB. So therefore we can describe the position and orientation of the vessel in terms of the positions of the point OB relative to the point ON. And then that vector, that position vector is expressed in this coordinate system, and that's what that P vector there means. Is the position, P is the position vector of the point OB relative to the point ON, and that vector is actually expressed in the coordinate system north is down, which is the inertial frame. So basically the coordinates are the north position, east and down. And then also we have the vector of Euler angles, which for marine systems, same as in aerospace, we use roll, pitch and yaw. And then we have the velocities. We have the linear velocities and the angular velocities. So the angular velocity is the angular velocity of the body relative to the inertial frame, and that vector is expressed in the body, fixed coordinate system. And then also we have the derivative of the position vector. That derivative is observed in the inertial frame, and then, which is that n here on this side, but then we express that velocity vector in the body frame. And the components of the three velocities are surge, sway and heave, and the components of the angular velocity are the roll rate, pitch rate and yaw rate. So, and then if we express the equations of motion in terms of these two variables, basically what we have is a kinematic transformation between the body fixed velocities and the derivative of the position and orientation. And then we have the kinetic model, which is basically based on Newton-Euler equations of motion. We have mass times acceleration. Because we are expressing the equations of motion in a reference frame that is not inertial, we have terms here due to Coriolis and centripetal accelerations. This has nothing to do with the rotation of the Earth. We are ignoring Coriolis and centripetal terms due to the rotation of the Earth. Then we have some damping forces due to the interaction of the vessel with the fluid. And then some gravity and buoyancy forces which provide the restoring terms that keep the vessel upright. And then here we have the vector of forces which are in the 6 degrees of freedom, which can be due to control, propulsion, and also environmental disturbances. And the advantage of expressing the equations of motion in a body fixed coordinate system is that the mass matrix, the inertia tensor component of the mass matrix, is constant. Another advantage is that in a body fixed coordinates, if we have an actuator located at a particular point on the vessel, it doesn't matter in which direction the vessel is oriented. We always know in this body in which direction the actuator is producing forces. So that really simplifies the control design. So that's why it's very common to express the equations of motion in terms of body fixed velocities, in terms of inertial velocities. Okay. Now, when we go to models for designing controllers for roller stabilization, the normal practice is to consider either a simplified 1 degree of freedom model, for which we consider only roll. And this is very common if you're going to design a control system based on fin stabilizers, based on water tanks, gyro stabilizers. It's very common to do that. However, if you try to design a control system using the rudder, then you might need to consider the model, which is a little bit more complex. So you may have 4 degrees of freedom. So you have the forward velocity, which normally is constant, so it's not. And so therefore you have only 4 degrees of freedom: roll, sway, yaw, and you can consider surge as well, because there are changes in it. So that's a model. Normally you have the control forces, and then we consider the motion due to the waves as a disturbance. And I will talk a little bit about that, why we do it that way. But let me specialize a little bit what these models are. So this should be a review for some of you. So we have for the first degree of freedom, 1 degree of freedom model, we have the derivative of the roll angle is equal to the roll rate. And then we have the rigid body inertia in roll times the roll rate. Derivative of roll rate is the angular acceleration. And then you have hydrodynamic forces, hydrodynamic moments, control moments, and disturbances can be due to waves and wind. So the hydrodynamic forces, normally we separate it into 3 components. We have some potential effects, terms. So due to the motion of the vessel, interaction between the vessel and the fluid, there are forces that are pressure forces that are proportional to the angular acceleration. There are also pressure forces that are linearly depending on the roll rate, and this is due to the waves that are radiated when the vessel rolls. You generate waves, and this represents the damping forces that take energy out of the vessel. Then you also have some viscous effects when you have some quadratic terms, but also you can have some linear terms used, for example, linear skin friction on the vessel. And then finally you have the restoring terms. So this is the simplest mathematical model that you can consider for designing and control system for a wall. When we go to a 4 degree of freedom model, then we consider as positions actually the angles, which is the roll angle and the heading angle, and then the velocities, you have the surge velocity, sway, roll rate, and yaw rate, and then you have the 4 forces, generalized forces. You have the surge force, sway force, the roll moment or torque, and the yaw moment torque. And then what you have is the rigid body equations of motion. So you have rigid body mass matrix, generalized mass matrix, Coriolis, and then again here you have the hydrodynamic forces, control forces, and disturbance forces. And similarly, as in the 1 degree of freedom model, the hydrodynamic forces, we have a component due to accelerations, components on Coriolis and centripetal terms due to the accelerations. You have damping and then restoring forces. So when you plug this term in here, you can then put some of these terms that depend on the state on that side of the equation, and then you end up with the model that we use for control design. The ocean environment. Normally we make simplifications to describe the waves. We assume that they are realizations of a zero-mean Gaussian process. This is valid only when you have very deep water. As you get shallow water, the wave elevation is not Gaussian anymore. It's also assumed that it's narrow banded, which means that the amount of frequencies that are contained in the waves is not too widespread, and that the process is stationary. And this means that the statistics of the wave elevation do not change too much. And this can be considered for periods between 20 minutes to 3 hours, depending on what conditions you are. So under all these 4 conditions, all the information we need is captured by the power spectral density of the wave elevation. And this is a function that depends on the frequency and also what we call the propagation angle, the angle in which they propagate the waves. So just from the power spectral density, what we can do is, for example, generate realizations of sea surface elevation. Now, for ship motion, for vessel motion, obviously the size of the waves and the periods of the waves are important. But something that is extremely important is the sailing conditions. And by sailing conditions, we define that as the speed and also at the encounter angle, which is the angle at which the waves propagate relative to the direction of the propagation of the vessel. So if the waves are coming from behind, we call it following seas, from the stern. The waves are coming from the stern, we call it following seas. Then quartering seas, beam seas, bow seas, and if the waves are coming from the front, this is called head seas. And what happens is that if you observe the waves from a stationary reference frame, which is fixed to the local geographical area, so then you will find that the waves have a particular frequency. But when the vessel is actually moving at a particular speed, what you have is like a Doppler effect. So if the waves are coming from beam Cs, then there's no Doppler effect. So you have the wave frequency, which is what you observe in a reference frame that is actually fixed to the earth. And then you have what we call the encounter frequency, which is the frequency that is observed by someone that is standing on the vessel. And if you're in beam Cs, you have a line with a slope 1, which means that whatever frequency you have in the stationary reference frame, you have exactly the same frequency that you observe there. When the waves are coming from the front or from the bow quarter, what you have is an increase in frequency. So if you have a particular frequency that you observe in a stationary frame, you have a little bit of a higher frequency that you observe on the vessel. And things become really interesting when the waves are coming from behind or from the stern, or they're coming in quarter and six. Because here, depending on the length, on the wavelength, you can have different effects. Because in deep water, longer waves travel faster. So therefore what happens is that if you have a very long wave, those waves will normally overtake the vessel, and then you'll be in this region over here. And then there is a condition for a particular speed and a particular heading relative to the waves. There is a condition here that if you are at that frequency of the waves, from the vessel you see zero frequency, and that's a very dangerous situation because it means that you're traveling right with the waves, and that can produce instabilities and broach to conditions. So it's a condition that sailors always tend to avoid. And then you have this region here of negative frequency. That means that there are very short waves, and those waves are being overtaken by the vessel. So this is like sailing from the waves from the stern, but going faster than the waves, so you're actually hitting the waves in front of you. So you experience like as if the waves were coming from the front. So it's a negative. That's what the meaning of the negative encounter frequency is. Now, how do we generate the motion induced by the waves? Well, here what we can do is sea-keeping theory models. So in sea-keeping theory, we consider that the vessel is not maneuvering, and what we do is traveling at a constant speed, and therefore what we can do is we can use solve the boundary value problem and try to determine for regular sinusoidal waves or a particular frequency, what are the forces by integrating the pressure on the hull, what are the forces of excitation of the waves. And then what we can do, once we have the forces, we can compute the motion. So this is like the frequency response function from force to actually motion. So there are 6 degrees of freedom, so you will have 6 forces, and then this G is a matrix of 6 by 6, and that takes into account the interaction between the different degrees of freedom. For example, if you put a force in a moment in pitch, that will produce the vessel to pitch, but when there is a coupling, unless you have perfect symmetry between fore and aft, there is a coupling between pitch and heave. So as soon as you pitch, you will have heave. So even though when you put a pitch moment, you will see a heave motion. And this is a typical model representation that you see in hydrodynamic books. So you see the rigid body mass matrix, the added mass matrix, which depends on frequency, and then you have the potential damping and the linearized restoring forces. So that's what these 6 matrices are. And for example, if we multiply F times G, what we get is the response amplitude operators. So we go from the sea elevation into the forces, and then from the forces to the motion. For example, if you want to get the response amplitude operator for roll, you need to get the rho number 4. Roll is the degree of freedom number 4, and then you multiply the 6 forces by the rho in this matrix, and that's how you get the roll graph. And for example, this is for a naval vessel, a patrol vessel sailing at 15 knots. So here we have the frequency, and here we have the different encounter angles. And we can see that when the encounter angle is 90 degrees, which is close to beam Cs, that's when you have the higher response in roll. One thing that we can observe is that it's really asymmetric whether the waves are coming from the bow or whether the waves are coming from the stern, and this is because of the Doppler effect. So these are the elements that are relevant to the design of the motion control system for roll stabilization or for roll reduction of vessels. So let's talk a little bit about motion control design. Talk about what are the objectives, what can limit the performance, and what are the different control strategies that can actually be used. So in terms of motion control, normally the way we do is we consider here either the first order is first degree of freedom, 1 degree of freedom model for the vessel, or the 4th degree of freedom, and then we measure motion, which can be the roll angle, and then we get the control that generates a command signal to the actuators, and then the actuators, due to the location on the hull, they produce a moment that tends to come. So there's something a little bit peculiar about this diagram, is that I'm considering here the open loop, what we call the open loop roll motions. Therefore, if the control is not active, if the control is not sending any signal to the actuators, then this signal is zero, and what you have here at the output is directly the control, how the vessel would roll if there is no control. And the reason for that is that we are combining here, especially for example for rudder roll stabilization, we are combining seakeeping models with maneuvering models. So what one could do is say, well, we can compute, instead of using the motion routes to generate time series of roll motion to put us a disturbance due to the waves, we could consider the time series of forces. But if you're doing that, you wouldn't be capturing the radiation forces very well, because the maneuvering model does not capture the radiation forces very well. So at the moment, unfortunately, we don't have simplified parametric models for maneuvering in seaway. We only have non-parametric models, so you can actually solve the boundary value problem at every time step in the simulation. It means that for every single time step, you need to solve the boundary value problem, get the potential, from the potential integrated using the Bernoulli equation to compute the pressure, integrate the pressure over the hull to get the forces, and then use those in the rigid body motion. And then you move into the next step of the simulation, and based on the next position of the vessel and orientation of the vessel, you need to resolve the problem. So we can do that computationally, but we don't have a parametric model that we can use for control design. So therefore, the best approximation that we can do is we consider our control design model here, which is mostly based on maneuvering theory, and then we use the seakeeping model. We use the RAOs and the wave spectrum to generate time series of motion, which we consider as an output disturbance. Okay? So if ladies interested, I can do another lecture on combination of seakeeping and maneuvering models, because there are interesting aspects to consider there. So, but if we decide to work with this type of diagram, so what we have is a closed loop system, and we can define a transfer function, because if everything is linear, we can define a transfer function from the disturbance in roll to the actual roll when the control is active. Okay? So this is called the output sensitivity transfer function, S. And what we have is that if this signal is random, which means that you have a particular power spectral density of roll, which again we can compute based on the routes. So if you multiply the power spectrum by the magnitude square of the sensitivity, what you get is the power spectrum of the roll angle in closed loop. And this is what can allow us to see how much the effect of the control is producing, is reshaping whatever spectrum of roll motion we have in open loop, what's the effect of the control, and how different is the shape of the roll motion in closed loop. But every time we have a feedback loop like that, there are limitations in what we can do. And if we consider a single loop where everything is linear, well behaved, and everything is stable, basically what we have is that there is an integral constraint that must be satisfied on that sensitivity function. And if you look at that integral, well, this shows that it's a balance of area. So if you actually reduce the sensitivity at some frequencies, it means that you have to increase them at other frequencies, because otherwise you can't balance the area. So this is what is known like a waterbed effect. So if you push the sensitivity down at some frequencies, it will pop up at other frequencies. And what happens is normally it pops up very close to the area where you're actually reducing the roll. And then you can define the roll reduction as 1 minus the magnitude of the sensitivity, and also if you want you can express that integral in terms of roll reduction, which means that it will be balanced. You can produce roll reduction at some frequencies, increase the roll reduction at some frequencies at the expense of reducing at others. Let me show you an example. This is a case of for a vessel in PMCs, and we're using a gyro stabilizer. So what we can see here is the response, the frequency response from the wave moments to the actual roll angle in open loop when the gyro is not active. And what we can see is as soon as we put the gyro active, we actually reduce. And if we continue reducing here, what happens is that it pops up the sensitivity here. That means that if you're using the roll angle, the gyro to stabilize, and we happen to excite the vessel at that particular frequency, the effect of the gyro is actually to amplify the roll. And you can see the same figure in terms of roll reduction. So in this particular range of frequencies, we have a very, very large roll reduction, about 90%. But if you move at low frequency, you can actually have a roll amplification. And the more you want to increase the roll reduction, the more you're going to have roll amplification at other frequencies. At high frequencies, it's usually not a problem because you're never going to encounter waves that excite the vessel at high frequency. The problem is the low frequencies, because as soon as you start sailing with the waves from quartering seas or head seas, the frequency at which the vessel is excited with roll can be actually very low. So you can very, very quickly end up in this situation where you turn the stabilizer on, and if the control design is not done properly or is not aware of this situation, you actually end up amplifying the roll motion instead of reducing it, so you have a counter effect. Okay. I mentioned a little bit the concept of no minimum phase dynamics, which was the thing we discussed for rather roll stabilization, so that inverse response. When you have no minimum phase dynamics, what happens is that you still have this balance of area, but you have a weighting factor here. And this weighting factor means that the balance of area is actually concentrated on a particular region of frequencies, which is close to what's called the no minimum phase zero of the system. So again, so you have a balance of area, but now it's concentrated at a particular range of frequencies. And this is, for example, what we obtain. Here is wave period. So here we are at low frequency, and here we are at high frequency. And these actually are frequency responses from design of a rudder roller stabilization from a Danish vessel. So they wanted to get a roll reduction of at least 50%. They wanted to be 50% over a particular range of frequencies. So you can't just obtain that with a single controller. So what they did is they have 4 different controllers, and the user can actually switch between the different controllers depending on what is the encounter frequency that the vessel is observing. But you can see that you're reducing the roll motion at particular frequencies, but you're amplifying that at other frequencies. And these other frequencies are very close to the frequencies where you're reducing. Okay? So that can produce a significant problem in roll reduction. I have a story of one of my colleagues was working for a shipyard, and this shipyard commissioned a university to design a control system for fin stabilizers. So the university designed the control system, they implemented, they installed it, they went on sea trials, and you turn the stabilizer on and nothing happened. And after the long discussions with the university, what was the problem, what my colleague did is just plug in a signal generator to the controller and went frequency by frequency, and he plotted the frequency response. And he realized that what the controller was doing is just it amplifies the roll motion, and then you have a very, very sharp notch at one frequency, and then again it amplified again. And then they spoke to the university, and the university said, yeah, but that's a requirement that the naval architect gave me. The naval architect said that the ship rolls at the natural frequency. So what I did is I designed a controller that eliminates the vessel natural frequency. But in reality what happens is that the vessels do not always roll at a natural frequency. So what this controller was doing is was killing energy at one frequency by putting it right next to it. So the net effect that you could see on the vessel is that it was not actually reducing the roll at all. Okay. So be careful with because very often you see in papers and in books that vessels tend to roll at the natural frequency. Not always. So and this is something. This is a simulation of a vessel that is traveling at the same speed on the same sea state, but different headings relative to the waves. So here is when the waves are coming through the quartering sea. So you have a long frequency, and in this case you have a small amplitude. Now we go to beam seas. The amplitude increases significantly. You got rolls up to 25 degrees. And obviously the frequency increases, so the period reduces. And here is when we go to bow seas. So again, the amplitude reduces a little bit, and there is a shift in frequency, not too much in this case. So as you can see, this is the same sea state and the same velocity, but you can see how much the spectral characteristics of the roll motion can change just by changing the heading of the vessel. And this is what produces problems in the control design, because in this case the power spectrum is at low frequency, and here is when you can have problems, because if this falls in the region where the system can amplify roll, you can be in trouble. So the design of the control system is actually is not as simple as it looks. So for fin stabilizers design, well, you can just use a simple 1 degree of freedom, and normally what you do is you map the lift that the fins produce it, you map as a moment, and therefore what you have is here is the roll moment due to the waves. Here you have the roll moment due to the waves. So you have the inertia and roll, the added inertia due to hydrodynamic forces. You have some natural damping. You have some damping due to the fins when they are actually inactive. And on top of that, what you do is you can add up the roll moment produced by the fins due to the changes in the angle of attack. So this is a simple model that we can use to actually design a controller. And controller methodologies that have been used in the past, H infinity and PID controllers. I'm not going to go into details on how to design it, but just the simple model that is used, and then you can look it up in the literature how these controllers are designed. One thing that is important for naval architects, sometimes they tend to design the vessel and then they call the control engineer to come in and do the stabilizer, whether it's an autopilot or a roll, and that sometimes works, but sometimes you can have severe deficiencies in performance. For example, if you put the fins far aft in the vessel, and the fins can behave like a rudder, and therefore you have this no minimum phase effect. Okay? So this is like a frequency response, a real and imaginary part, a Nyquist diagram. Whatever is in blue, it means that there is, you start at frequency omega 0, you increase in frequency, so there is a range of frequencies from this frequency to this, in which there is roll reduction, but at high frequency and at low frequency, there is actually roll amplification. But a simple design, when you put the fins a little bit forward, can actually get rid of the problem at low frequency, so that problem disappears. So just a small change in the location of the fins can significantly simplify the task of the control design. And I was involved in a project with a vessel that they put fin stabilizers, and what happens is that in quarter seas it created a lot of interference with the heading. And they thought at the beginning that it was something related to the shape of the hull, so they spent a lot of money and time tank testing the vessel to see if there was a problem with the interactions, and there was no problem. It's just that the fins were too far aft, and therefore they were producing this no-minimum phase effect, and the controller was not designed to actually take this into account. So what they had to do is, in order to improve the performance, they had to put another pair of fins that actually counteract that, and they were only using Corten or head seas. And the consequence of that is that you reduce what the fins could actually do in terms of performance, and because you have to add 2 more fins, they have an increase in drag. Okay? So just a simple things between the interactions between the design of the plant, the design of the system, and having a bit of knowledge of how this will affect the controller can actually save a lot of money and time down the track. Fin stabilizers are also interesting in one other aspect, is that of the stalling characteristics. So you know that if you have a foil, a hydrofoil, and if you put it in the cavitation tank, if you increase the angle of attack, you will increase the lift, and then eventually the flow will separate and the lift will break off, and you will have stalling. That's fine, but when these fins are actually operating dynamically, not in steady state at a particular angle, but all the time, what's happening is that the vortex sharing and the pressure distribution again can produce a stall, but the stalling condition is significantly different than what it is in steady state conditions. So here we have data from some experiments. You move the fins between 13 degrees and plus 13 degrees, and you have the effective angle of attack and the lift coefficient. But here, if you go about 25 degrees, you'll see that, well, if you increase the angle of attack, it actually stalls. But the problem is that when you reduce the angle of attack, the flow does not reattach. So it's not that it's coming back on this curve, it actually comes back that way. And for example, here you can see that you have negative lift. And they run these experiments in the Netherlands because in some cruising vessels they were finding that the stabilizer fins were actually bending forward, which means that the vessel had negative added resistance. And it was because of this effect, which is the dynamic stall. Another significant effect was that the vessel motion in roll was actually very small, about 2 degrees, and then all of a sudden you get 7.5 degrees of roll, and then again gets reduced. And this was the effect that the controller induced on roll. So what I did is I reproduced these results in simulation. These are in my book. And what we have here is the roll angle, roll rate. This is the mechanical angle of the fin. This is the effective angle of attack of the fin. And this is the lift. And we can see that there is very good roll reduction. And then all of a sudden, when we hit a big wave, what happens is that we have a lot of roll. The controller pushes the fin, so it tries to develop as much mechanical angle as it can. The more it pushes, the more it stalls, so the lift goes almost to zero, and for a period of time the vessel behaves as if there's no control at all. And I had a chat once with one of the captains of the Australian patrol vessels. He told me that in the old patrol vessels they had, in severe sea states, they used to switch the stabilizers off. I said, okay, why do you do that? He said, well, if you switch them off, you have a lot of roll, but you can adapt to it. So after a while, you get used to it and you know how to position yourself and how to move and continue operating. Whereas if you put the stabilizers on, yeah, you have low roll reduction, but then all of a sudden we have these increases in roll, which we can't predict. So and if they happen very frequently, like here, you have 150 seconds, and again 50 seconds later, he said that becomes very annoying to operate. So we decided to switch the controller off when we are in a high sea state. So this is part of some work we did in 2003. And what we did is we proposed a controller that actually estimates the effective angle of attack and puts a constraint such that the effective angle of attack is less than the steady state stall angle. And this is exactly the same simulation scenario, but we can see that now, when the big group of waves come in, we actually don't have that effect. Okay? As far as I know, this hasn't been tested in practice, so this is only done in simulation. Okay, so in terms of rudder roll stabilization, I think I discussed a little bit of some of these aspects in the history. when you're using rudder roll stabilization combined with fins, it is always good to actually coordinate the two. So the integrated rudder and fin control was proposed in the 1970s. And then most of the work in rudder roll stabilization, most of the successful applications were done in the navies, in the Netherlands, in Denmark, Sweden, and the UK in the 1980s. So yeah, so this is, for example, some of the effects that I've been talking about, the waterbed effect, that if we would like to reduce the roll sensitivity at a particular frequency, what we will have is normally the roll reduction will be negative, or you will actually increase the sensitivity at other frequencies. And there are some formulas to predict. Well, depending on how much you want to reduce this, to predict a lower bound for those peaks, which means that you're going to have amplification of something that is greater than that value. So there are some formulas to predict that. The effect of the non-minimum phase dynamics, it's also evident in terms of roll reduction. So for example here, in some work I did, I look at optimization-based control. So I want to optimize deviations in heading, square, versus reduction in roll, and weigh the two of them. And what we do is, as we increase the value of lambda from 0 to 1, which means that we start focusing more on reducing the roll, so E there is the expected value. As we start, even if we just concentrate only on reducing the roll, there is a limit of what we can do. So here is the roll angle in RMS, and here is the interference with the heading. You can see as we take lambda from 0 to 1, we're reducing the roll, and the price we have to pay is that we're actually interfering with yaw. And even if I only care about roll, there is a limit. I can't reduce the roll to 0. And this limit is given by the non-minimum phase dynamics of the system. Okay? So there will be no vessel, for a particular vessel design, you will never be able to be below this curve. Another aspect that is important for rudder roll stabilization is the rudder machinery. Sometimes the control system might be demanding too fast rates for the rudder. And what happens is these simulation experiments where we have a rudder machinery and we excite it with a sinusoidal of a particular frequency, and we start increasing the amplitude. And at the beginning it's fine, but then as the amplitude becomes larger and larger, if you have limits in how fast the rudder can move, you can see this effect of saturation of the machinery. And what's important for control design is, if the signal in blue is what the controller demands, the controller wants the maximum angle here, and it's actually getting the maximum angle a little bit later. So there is a lag, and that lag can produce significant degradation of the performance of the control system. So you have to be very careful, because these sometimes can reduce performance. One way of solving the problem is to use what's called an automatic gain controller. This was proposed by Professor Van Amnogen in the Netherlands. And this is similar to what radio receivers do. When you're very close to the station, they reduce the gain. And when the amplitudes the amplitude demanded are too big, you have to actually reduce. The advantage is that, well, you're limited in the amplitudes that you can do, but at least they are in phase. So therefore you don't have the phase lag, so this is convenient for control design. I mean, there's nothing you can do if you have a limited rate actuator. You won't be able to move it faster than its rate limit. But at least what you can do is just to keep it in phase. So the amplitude will be reduced, but they are in phase. And here is the similar curve that I showed you before, when you have the limitation due to the non-minimum phase dynamics. But when you add on top of that the limitation of the rudder machinery, you can see that in this case the rudder machinery dominates what you can do with roll. So in some cases it is the rudder machinery what limits the performance of the system. So this is for the case of, again, it's a patrol vessel, It's a 50-meter patrol vessel. It's in sea state 5, 4-meter waves in beam seas. Now if you take the same sea state, but if now we move to port turn seas, what we have is now, well, the two curves are more closer together. Because when you're in port turn seas, the limiting factor in this case tends to be the non-minimum phase dynamics more than the actual rudder machinery. So something to remember is that at low encounter frequency, the rudder body stabilization versus yaw or heading interference is actually can be large, and this is dominated by the non-minimum phase dynamics. And if you have high encounter frequencies, normally it's the rudder machinery what limits the performance. Okay, so this is an example of a simulation. The vessel is in quarter in seas on 4-meter waves. And you can see the roll angle reduction, and here we can see the rudder angle. So here we can see the heading angle. So we can see that we reduce the roll, but the price we have to pay is that we actually increase the heading disturbance. And here is the roll angle that is well below the maximum limit, sorry, the rudder angle. This is way below the limits at which you can move the rudder. So in this case, this performance, the maximum performance you can achieve, which is a roll reduction of 40%, is actually limited by the dynamics of the vessel, not by the roll machinery. Now, if we are on the same condition, sorry, it's even less, this is 2-meter waves, but now if we are on beam seas, we can see that, well, we have a better roll reduction, but now we are hitting the saturation of the rudder. So we're moving the rudder up to plus minus 20 degrees. And in this case, and also in some cases, we have rate saturation. And this is what actually limiting the performance of that. It's not the non-minimum phase dynamics. Okay. So controller strategies that are used for designing this type of controllers can be PID controllers, H-infinity, loop shaping, which are all frequency domain, adaptive linear quadratic gain controllers, model predictive control. Some people use switch control. Depending on the sailing conditions, you can switch between different controllers, or some people have proposed non-linear control. However, the problem is mostly linear, except for the saturation of the rudder machinery. I will skip that one. And this is the case. This is, for example, a controller that was proposed by Blanke in the 1980s for the Navy patrol vessel from the Danish Navy. And he was the one that they wanted to achieve at least a 50% roll reduction in a particular range of frequencies. So they designed 4 different controllers, and the pilot can actually switch between them depending on the wave encounter frequency. Okay. Let me talk a little bit about, I will skip the gyro stabilization, but just to show you a little bit of performance. This is some study that we did for a patrol vessel, for a Navy patrol vessel, and we get roll reductions in the range of 80%. So that's roll reduction in angle. And then we also get significant roll reductions in acceleration. And this is the moment that the gyro produces on the vessel. So we can see that the performance is quite good. And in this case, the control system we design adapts to different sailing conditions. When the encounter frequency changes, the control system on the gyro actually changes. Okay, so this is an overview of some of the techniques that are currently in use. Now let me talk just a little bit about a bit of a research outlook. What some new devices that have appeared in the few years, just in the later years, and then some problems that still remain to be solved. One of the problems, and this has been mostly inspired by or pushed forward by the luxury yacht industry, is the stabilization at 0 speed. So we have the gyros, which are a good option for that, but then there have also been proposals for flapping fins. So basically you have a fin, but you put the shaft of the fin really forward, so therefore the fin becomes like a flipper. The fins become like a flipper. So when you are at 0 speed, what you can do is just flip the fins and then wait a bit of time and then flip them again. And therefore, once you change the angle of the fin from minus 30 degrees to 30 degrees as a function of time, what you have a peak of a hydrodynamic moment in roll. First, due to added mass. You know that when you move in water and you want to accelerate fast, which is the point here, we have the maximum acceleration. You have actually force, and then there is obviously vortex shedding, which is what dominates the force again. So you can see that for a particular period of time, and normally these two cancel each other. You have some forces due to vortex shedding that you can use to counteract the motion. So the idea of this is that you flap the fins, you wait, and then you flap the fins again, and then you can use that to stabilize the motion at 0 speed. So this is something that there are some companies that are actually now advertising this type of stabilizer. Another type of stabilizer are rotor stabilizers. So basically this is simply a cylinder that is rotating and that takes into account what's called the Magnus effect. So if you have a cylinder in a potential flow, normally you have a distribution of pressure such that you have a high pressure at the front and the low pressure at the back. However, if you make the cylinder rotate because of the boundary layer, what happens is that the speed increases at the top if the cylinder is rotating clockwise, in that case. So you have the speed of the fluid coming in and the cylinder rotating that way. In that case, the speed increases, and at the bottom, because of the interaction between the boundary layers, what happens is that the flow reduces. So when you have reduced velocity flow, you have high pressure. And at the top, where you have increased velocity of the flow, you have low pressure. So you end up shifting the pressure. So you have more pressure at the bottom than at the top. And therefore, by rotating these cylinders, what you can do is create a moment as well. And I've also seen some applications of this type of devices, even at 0 speed. So they actually rotate the rotors, but also flap them back and forth. And then you can do stabilization at 0 speed as well. Okay? So these are some of the devices that have appeared in a few years. There's not a lot of work that's been done on control, but there are interesting effects there to study. And finally, I'd like to talk to you a little bit about a phenomenon which is called parametric resonance or parametric roll. And this is an effect that has been observed in the latter years on particular type of vessels, in which the roll motion is very small, but then all of a sudden the roll motion grows very, very rapidly. So in a few seconds you can go from 2 or 3 degrees to 15 or 20 degrees. This can be significantly dangerous for large vessels. And this effect is noticeable when the vessel is sailing against the waves or with the waves from the stern. So let me show you a little experiment that was done at the University in Tasmania. So here we have the vessel in the ocean basin. This is a model of a 300-meter container vessel. It's sailing forward with the waves, and then if you look at the bridge, you can start seeing the rolling. The vessel start rolling, and very quickly develops a very high roll. So these have produced a lot of damage in container ships and insurance companies as well. So this effect basically is triggered by a combination of things, but the key aspect from the naval architecture point of view is the design of the hull. Because this appears for hull designs that have significant bow flare and overhang sterns. And when you have that type of hull, what happens if you have sailing conditions in longitudinal waves, which you're having against the waves, depending on the location of the wave along the hull, you have significant variation in the water plane area. And that changes the restoring characteristics of roll. So this effect of rapid increase in roll motion appears when you're sailing in longitudinal waves, the wavelength is the same length of the vessel, and the encounter frequency is twice the frequency of the natural frequency of roll. And also you have a vessel with low damping, like a container ship or a bulk or a cruise ship. Yeah. So what happens is, so here we can see something that you're used to. That's the GZ. That's the stabilizing the righting arm. So you have center of buoyancy and center of gravity, and as you increase the roll angle of the heel angle, you increase the GZ. And what happens is that because of the shape of the vessel, when the wave crests are in the bow and the stern, because of the shape of the vessel, you have a very stiff vessel. So as soon as you disturb in a roll, you have a very large displacement of the center of buoyancy. So you move along this curve. So as soon as you try putting roll angle, you get a very strong moment that tries to bring you back to the equilibrium position. But when the wave is amidships, the situation is reversed. You have a very soft restoring moment. And that's when you move on this curve. And what happens is that the vessel rolls and the wave increases the pressure in the bow and therefore produces a moment. By the time the vessel has most of the kinetic energy, the wave coats amidship, and therefore what happens there is that there is no restoring moment, so the vessel builds up its rolling motion, and that's what happened in the beginning. Okay? So this is something that is creating a lot of problems. There's been, in the latter years, there's been a few people at university looking at how to detect, do an early detection of parametric resonance. There is some software available to avoid routes where it's believed that because of the storms and the heading angles that we have on the route, that the vessel could experience that. And there's been now some guidance on how to avoid those conditions. Because in the past, people used to slow down, but actually, when you slow down, you lose controllability of the vessel, and the best thing is to speed up. But it takes a bit of courage when you start building the roll angle to actually speed up. Okay. So, in conclusion, so this is probably a bit at the end of my presentation. The problem of roll motion has been going on for about 100 years. The later device that was proposed was the rudder for simultaneous roll stabilization and course keeping. That was in the 1970s. Then from that time onwards, there haven't been many new devices proposed until now, very recently, where we have the flapping fins and the rotor stabilizers. Most of the stabilization devices require control, and the control design is far from trivial because there are fundamental limitations due to the dynamics. The wave-induced motion can change in frequency significantly with the sailing conditions, and that creates quite a bit of problems in the design of the control system, and sometimes you have actuator limited authority. So when you combine these three effects, the design of the control system is not trivial. And sometimes the decisions that are made by naval architects on where the actuators are located can have a significant bearing on the performance. So when you are designing a vessel that requires motion stabilization, it would be good to involve from the beginning or at an early stage in the design someone with knowledge in control systems and system dynamics, because it can really simplify the task and obviously improve the performance as time goes by. There have been new developments. Currently, some of the navies are pursuing again the use of rudder roller stabilization. There are some problems as well with submarines that require a stabilization at low speeds when they are in the surface. Now, what are some of the problems that are still not quite solved? Adaptation to changes in sea state and sailing conditions. This is a problem that is not quite solved yet, at least in the open literature. Maybe some of the companies that produce stabilizers have solved it. They have new devices with very interesting hydrodynamics, and there haven't been much work done on that, except for some industries. So therefore, it's not open in the literature. As I mentioned, integrated vessel design and roll control design can be very important to ensure high performance. And also, you have to be careful of parametric roll. If one tries to optimize the shape of the hull for resistance, then you may end up with problems of parametric roll. Okay, I'd like to thank you for your attention. I hope I have given you a broad overview of some of the issues that are related to control design in terms of roller stabilization, and I hope you enjoyed the lecture. I can be available via email if you have some questions and things. Okay, thank you very much.